Robert Weismantel.
So now a different topic. We move away from continuous optimization and have a look at the discrete world. And there, in the past years, this field of nonlinear mixed integer optimization somehow came up, and a lot of people work on this currently. So one thing is we want to extend some of the theory from the linear integer case to some classes of nonlinear functions. And so this is exactly in this direction what I'm going to present today. This is joint work with Alberto Del Pia. So what is the problem we look at? So it's integer polynomial optimization, which is the following. Given is a polynomial function, and k here indicates the degree of the function. And we want to study the optimization problem, minimize this polynomial function over the integer points in a polyhedron. And when I speak about a polyhedron, I always mean a rational polyhedron. And in fact, for this talk, I will restrict myself even to polytops. So this is the bounded version. Okay? So that's the type of problem. And in fact, it's quite interesting to look at this complexity table of integer polynomial optimization. So here, the matrix that you can see here has these two parameters. So on the one hand, it's k, which is the degree of the polynomial, and then n, which is about the number of variables. Now, first thing is that if you look at k equal 1, so then we are in the case of linear functions. And there, you know, from the complexity point of view, the maximum that we can achieve is a polynomial time algorithm when the number of variables is fixed. This is this Lenstra theorem. If the number of variables is arbitrary, then in general this problem is, of course, NP-hard. So now, if you look at the really polynomial case, then you move away from the linear setting. And so this is when k is equal to 2 or 3 or 4. And there, what is not so difficult is indeed to work out when you only have one variable, then you can solve this problem in polytime. So the interesting case begins when the number of variables is equal to 2. And there, in this paper that I think also Jesus mentioned in his talk, so this is this paper, we showed that, in fact, it's quite easy to take a number theoretic question with which you can prove that the problem is NP-hard when the degree of the polynomial is 4. And in fact, what is really striking is even if the polyhedron is a box. So the integer points in a box, this is the feasible domain, and now you would try to optimize a degree 4 polynomial. This is NP-hard. So the open question, and this is exactly what motivated this talk, are these question marks in here. So one thing is when n is equal to 2, what happens if you take a degree 2 polynomial, which is a quadratic function? And I want to show you that this you can do in polynomial time. Then it's interesting, really, to go a little bit beyond, and this seems to be very, very difficult. So there's something very interesting going on from the complexity point of view. In fact, usually, if you can prove that a problem is polytime in dimension 2, so with 2 integer variables, you very often manage to prove a polynomial time algorithm when n is fixed. So maybe this type of problem is exactly the case where this really breaks down. So I'm not sure really what happens if you take 3 variables. So this is the point of view from the, so this is the complexity table. And maybe I'm allowed to say this again. So this paper here indeed showed that if you maximize a positive polynomial over the integer points in a polyhedron when the dimension is constant, then this you can not do exactly, but what we achieved was a so-called fully polynomial time approximation scheme. So you could get an algorithm that approximates this problem, but you had this kind of technical properties like f being positive on the domain and so on and so forth. So far so good. That's the complexity. Now maybe for those people that are not so familiar with this integer world, let me put up a little slide to show that in fact these integer polynomial problems in low dimension are very, very related to number theory type questions. So the first one is this problem N1, which you can find in Gary and Johnson, which is of the following flavor. So given three positive integers, a, b, and c, does there exist an integer z smaller than c with the property that z squared is congruent to a modulo b? So that's a number theory type question. And this indeed you can turn into an optimization problem of a degree 4 polynomial over the integer points in a box. And this is, in fact, the proof why this problem is already NP hard. And then another one, which is also nice, is this Pell equation, which I'm sure many people have heard here about. So given is a number n, and what you search for is integers, without loss of generality, positive integers, so that you can satisfy this quadratic equation, x squared is equal to n times y squared plus 1. And in fact, here there's a very interesting phenomenon. So such solutions exist, but the catch is that the encoding length of these solutions is very, very large. And so this is really where complexity enters. And that, of course, has to do with the irrationality of numbers. And so as Bernd, I agree. So the irrationals we are a bit skeptical with. In fact, this will also play a role here. So now I think I'm prepared to show you this result. If k is equal to n is equal to 2, then I claim we can solve this problem in poly type. So from now on, I will, in fact, look at this general quadratic form in two integer variables, x and y. And this is the convention for the coefficients, so ax squared plus bxy plus cy squared plus dx plus ey. And p, as I said in the talk, I will restrict myself to the bounded case. So the unbounded case is more involved. So, and what we assume is that this polyhedron is given by an outer description. So we have an inequality description of the polyhedron, ax less or equal to b. So now, what are the main ingredients? And that's what I really want to convey, and I want to show you how to really take these two things. So we need two major kind of things, which, yeah?
I'm confused, but so why isn't this contradicted? I mean, if you want to factor a number into a quadratic program in dimension 2.
Mm-hmm. Why doesn't this contradict this? This you cannot write as a quadratic.
So if I want to write a times b equals something, and I want to find a and b as factors.
Yeah.
So that's a quadratic integer program in 2 variables.
Wait.
This is degree 4. You need to, because you're talking about factorization, factorizing, right?
Yeah.
Yeah, the problem
So look,
can be more
exactly. So the key is you cannot take arbitrary quadratic equations and handle them. This will lead to degree 4. That's exactly the thing. Okay, so exactly. So exactly. So now, so before I illustrate these main tools, let me just go a little bit through this standard notation, but I will use that throughout. So we'll speak here about conic sections. A conic section is of the following type. You have this quadratic, and you set it equal to a given value of gamma. And then you can classify geometrically this conic sections. So in particular, if delta is smaller than 0, then the equation represents an ellipse. And if delta is equal to 0, you get a parabola. And if delta is positive, you get a hyperbola. So that's the kind of, that's very well known. And in fact, what I also need is degeneracy. So degeneracy, we'll call a conic section degenerate if we have the property that this value gamma here is equal to 0. And in fact, the name degenerate comes from the fact that if you look at gamma equals 0, then ellipses just become points, parabolas turn into parallel lines, and hyperbolas turn into intersecting lines. So now here are the main tools. So the first one is very simple concave lemma. So take any rational polytope in Rn. And let fk be any function with the property that if you take an arbitrary point, z bar in P, then the set of all z in the polyhedron whose objective function value is greater or equal than the given objective function value is convex, Then, if the number of variables is fixed, you can solve this problem in polytime. So how can you do this? This is very, I mean, you have to know the tools. So the thing that you can do is in fixed dimension, you can do the following. So we can first compute the set of vertices of the integer hull of our polyhedron. So once you do this, then you simply go through the vertices of Pi, and in fact the number of them is polynomial in the encoding length of P. That's the property that we have in fixed dimension. This is very important. That doesn't hold, of course, in general dimension. So what you can do is you take the best vertex, so the one that attains the minimum function value, and then you can write down W, which is just the set of all Z, whose objective function value is greater or equal than the given objective function value, f of z bar. And this is by definition a convex set. Now, by definition also, since you chose the point in among your vertices that attains the minimum value, the property is that this set here has the property that it contains all your integer vertices. But then, since W is convex, the convex hull is also contained in W, and therefore this shows that if you just take the minimum, the vertex in your convex hull that attains the minimum value, this is indeed a minimizer. So that's one property that we use. Now, a second property is an extension of a Lensstra's algorithm, and this is an algorithm due to Katjan and Porkolab, where you have the following property. So you look at convex sets with the property that you can write down this y by polynomial inequalities in integer coefficients. So given this description of your convex set, so you need the property that the set is convex, and you need the property that you can write it down as the intersection of finitely many polynomial inequalities. Once you have this property, then in fact what you can do is that if the dimension is fixed, you can decide in polynomial time in the encoding length of your given set whether the set contains an integer point. And that's an extension of Lensstra's algorithm. And then from this, it's very clear that you can also tackle corresponding optimization problems where you minimize G0 subject to Gi of z less or equal to 0 under the assumption everything is convex, of course. This is what we need. Now, for a general quadratic, of course, this function is not, well, this is neither concave nor convex, and so we will now have to take these two main ingredients, the concave lemma, and this kind of convexity result over integers, and combine them in an appropriate way to get to the problem. So that's now the plan. Okay, so these are the two ingredients. And so now I'm prepared to begin with the easy case. The easy case is when this delta, so this b squared minus 4ac is less or equal to 0. So we proceed as follows. So if a is equal to c is equal to 0, so a and c were the coefficients in front of the squared terms. So ax squared and cy squared. If both of them are 0, then it's very trivial that b is equal to 0, and so everything is linear, and we can apply Lenstra. This is completely clear. Now, the nice property is, in the general case, we can assume without loss of generality that a is different from 0, and so this allows me to rewrite this function as a function like this. So here we have a in front as a coefficient, we have a squared term, we have y squared with this expression, and we have these linear forms here. So here's the nice thing. Since delta is negative, we have the property that the two coefficients here and here in front of the squared terms are compatible in sign. So if a is strictly positive, then also this thing here is non-negative. And so what you get is a convex function, right? Because those coefficients are positive, of course. And so now we can solve this problem with this Katjan and Porkolab algorithm. If both a is negative, then this implies that also the second coefficient is less or equal to 0. And now we have here a negative coefficient in front of the squared terms, which shows us that this is a concave function. And so with the concave lemma, by computing the integer hull for the vertices, taking the best one, we can solve this problem. So that's the easy case. The more involved case is the delta positive case. Now, when delta is positive, we can assume without loss of generality that in fact A is positive, because if A is positive, this thing here is negative, and vice versa. So we have now a mixture. We have a positive factor in front of the square, and we have a negative factor in front of the square. And now this kind of combination we need to handle. So now, the first thing is, after again rewriting this function in this way, we see here that there's a constant that pops up. And so now it's very clear what the degenerate case is. So the degenerate case happens to be the case precisely when gamma bar equals this expression here, right? Because then you have the property that this here is equal to this here. So you get two square terms. Now if you take roots on both sides, then you get these two intersecting lines. That's exactly the degenerate case. If you don't see it, believe it. But that's in fact exactly what happens. But what you also already see is, and this is where a problem comes up, if you try to do this explicitly, you have a problem, because now we get this irrational data. And we don't know what to do with this irrational data. We cannot write it down. So, and this is in fact a problem, but there's a very, very beautiful property that at the end helps us to really get over this. So this is the degenerate section, and so it's not important. From now on, I call this gamma bar. This is our degenerate section. And now we look at the structure. How does this thing look like? So the first thing is, I said we have to be a little bit careful. When we look at this degenerate section, we get these two intersecting lines, but we cannot explicitly take roots, so we somehow have to handle that algebraically. We store this information somewhere, and we don't explicitly take the square root operator. Now, here's the property. If you take these two lines, then what we see is this gives us a nice subdivision of the space of R2 into these four polyhedral regions. Unfortunately, as I said, not rational, but still polyhedral. So this is the first part. So this is P1 and P2. They are like this. And here we can, it's not so difficult to show that, in fact, the function value here is strictly less than gamma bar. This is a little exercise, and you see this is exactly going to happen when you lie in this region or in this region. And symmetrically, the function value is greater than this degenerate value gamma bar in this region and in this region. So, and now we have a nice property, in fact, two nice properties, which are also symmetric on P1, P2, and P3 and P4. Because if we now take any value gamma less or equal to gamma bar, then all the points that satisfy that their function value is less or equal to gamma, less or equal to gamma bar, this is the union of two convex sets. So, and symmetrically, in these other two regions, we just have to reverse the signs. So for every value of gamma bigger than gamma bar, this set is also the union of two convex sets. And now we somehow have to handle them. So here's what we do. And the sequence is important. So we look at these four regions, and now we solve this quadratic programming problem. We intend to solve this quadratic programming problem over Q1 and Q2. If there's no integer point in the union of these two sets, then I claim we are done. So, well, if we, excuse me, the converse, if we have an integer point in the union of these two sets, we are done. Why? Because we want to minimize this objective function, right? So if we don't want to be completely inefficient, then let's first look at these two regions, because if there are points, they are definitely superior to what the points are there. So in the other case, we know this property holds. And this is a very, very important property. Only because this holds, we are then able to solve the problem over Q3 and Q4. So it's the sequence, which is also important. So this is the illustration, how we proceed. So now the first thing is, let's look at these two types of regions, the Q1 and the Q2 and the Q3 region. So for the first region, we want to apply now Katjan and Pocklak's algorithm in a binary search setting, which you can do quite easily. You find an upper bound, certainly less or equal than this, and you also can compute a lower bound by individually bounding these monomials. So imagine I was assuming P is a polytope, so I can write down some bounds. And here we have this nice property, as I said, that the set of all xy, so that f of xy is less or equal to gamma, and gamma is smaller than gamma bar. This is the union of two convex sets, one contained in P1 and the other one contained in P2. So far, I cannot apply Katjan and Poklak because it's the union of two convex sets. So what do I need to do? Well, the problem is that the constraints defining really this Q1 set might not be rational, right? Because the lines have these irrational coefficients. So now, what we need to do, and this is what we can do, we can construct an inequality with integer coefficients, which is valid for P1, but not valid for any point in the interior of P2. So in other words, this union of the two convex sets, we now construct a nice hyperplane that separates. And if we do this, then we end up, for each of the sets, Q1 and Q2, with a nice description. Namely, we can take these polynomials, together with these separating hyperplanes, have a convex description with polynomials, and then solve this problem with binary search type methods. So in the other case, when you do this, when you inspect this problem over Q3, I told you there are two things. So one thing is, and this is really very important, is that we now utilize the fact that Qi intersected with set 2 is empty. So we know that in these two regions, there's no integer point. Now, and then we will apply the concave lemma. So in fact, the easy thing is, again, if Q3 happens to be rational, then what you can directly do is, since there's no point in Q1 union Q2, and you have the property that these sets here are convex, this is what we have shown in these regions, P3 and P4, or Q3 and Q4, we have this convexity property. So now we are directly prepared to apply this concave lemma. However, to apply the concave lemma, you remember we have to do an integer Hull computation. But an integer Hull computation we can only do if the description of our polyhedron, so now we need linear inequalities, first of all, and we need nice coefficients. And this is true if Q3 happens to be rational. This is very easy. Now, in the other case, when Q3 is irrational, so now we need to do the following. Now we construct an inequality, which is, again, a linear inequality, with the property that it is valid for P3, but not valid for any point in the interior of P4. And now, since Q1 and Q2 have no integer points, I have a nice description of my region. Namely, I can drop all these conditions and just write down the linear inequality. Yeah? Q1 and Q2 have no integer points inside. So we don't need these polynomials at this stage. And now we have a linear description. So we are in the polytope case. And so now we happen to get a nice polytopic description, and we can apply this operator that computes the integer Hull. And with this, we are done. That's the way to do it. So it's a sequence of arguments. You need some, you need this, of course, the convex case is a very important subcase. You need this concave thing. You need the integer Hull computation. So if you think about it, even in this case, you need much, much more than linear inequalities. And so there was, we had a little bit this discussion, can you really reach very much if you replace some of the linear inequalities with quadratics, higher order polynomials? I think you really have to be careful. Even in this little case, you see how much more machinery you need. Integer Hull computation is much, much more involved than just optimizing a specific linear function over the integer points in a polyhedron. In fact, I said this is technical. We can also handle the unbounded case. And for the unbounded case, the first thing that you would really like to verify is if I give you this kind of quadratic, and now I have an unbounded polyhedron, is this function bounded? over this unbounded region or not. And there you can write down some conditions that essentially tell you that it's enough to really look at the recession cone of the polyhedron. So the polyhedron has a recession cone, which are all the directions with which you go to infinity. And so now it's quite intuitive that you think if there is a sequence of points that goes to minus infinity, then there should be a ray along which you go to minus infinity. And that's exactly what happens to be true in this particular case. And you can also test these conditions and then extend to tackle the unbounded case. And with this, I come back to these two questions. And now the only thing we did is that we plugged in here this little p. This is what I tried to show you. There are two question marks now, rather than one in the very beginning, because this is exactly where we are working on. And it's very difficult. I really think it's very difficult. I don't know. So anyhow, the thing is, if you take three quadratic forms, all this machinery breaks down completely. Why? Because look at one key element was we were inspecting this degenerate section. And there we happen to have a polyhedral description with irrational data, but still we had these lines. Now if you look at more of these forms, and you try to look at the degenerate section, you do not get a polyhedral description. You get this kind of weird curves. So now you get quadratics. For quadratics, you cannot take now the integer hull and believe that the number of vertices is of polynomial size. In fact, in general, it will be of exponential size. Even if I could do it, which nobody knows how to do it, but even if we could, the number of these points would be exponential. So you need really something quite intelligent. And then what is very interesting, after a couple of transformations, you see the key thing is there are these residue classes that pop up. Residue classes between the coefficients, so something like a plus b modulo c, all these kind of things pop up. And so if a, b, and c are large, and that's always our assumption, right? We encode, so they're coefficients. So so here in this computational model, we assume that you input the coefficients a, b, c, and so on. So the number of bits that are required to represent the number is of logarithm of the numbers. And so if now the modulo classes pop up, and for each modulo class something else happens, then this will not lead you to a polynomial time algorithm. So I'm really not sure whether you can do it. We also work on this problem where we make some progress, but in fact it's slower than I expected. Somehow it's embarrassing, right? We deal here with dimension 2. I mean, we want to do something for general n. But even from the point of view of computational complexity, we have to be a little bit more careful. And I honestly also strongly believe that we have a beautiful theory nowadays about these low-dimensional integer programming problems. And this is a key question. We need to build the bridge from general dimensions in integers to these low dimensions. So you see, in general dimensions, for an integer problem, you typically think about a binary problem. And I see this in all the presentations. So if people speak about integers, they think integers are typically 0, 1, which is true from the practical point of view. But here, the entire mathematics is in this setting where, in fact, the range of a variable, so a variable can attain a huge range of different values. And this is really where a lot of mathematics you can do. And we will build this. I'm very confident that we will try to find a way to really bridge this gap. And this is then entirely, at the end, hopefully also not completely irrelevant from the computational point of view. So thank you very much. This is it.
One question. One case I somehow was missing. Isn't it possible that you have not unboundedness to minus infinity, but boundedness, but you don't get the payment?
Yeah, but this is exactly what you can handle. I didn't speak about the unbounded case. It's really very technical. And my main thing was I wanted to convey this kind of building blocks that you have to put together in the right sequence to tackle the case. And for this, I think the bounded case is already quite nice.
So, so the proof is using a mixture of convex analysis and the dimension tool, right? Because if you go to higher dimension, do you think that because it's kind of a miracle, no? Using those two lemmas that you are presenting, or use this sub-level set which is convex.
Mm-hmm.
And do you think this convexity argument could help in higher dimensions, or?
Yeah, but I told you, Chauberna, one big problem is, even if I have convex sets, and now I look at the integer points in convex sets, I don't know how to compute the integer hull. First of all, even if I could, the problem is that the number of integer points could become exponential. So this is the key element. I mean, some of the things go through, it's true. I looked at it, I worked on this for 4 weeks because I thought, hey, it's not impossible. I mean, if you do it for n equals 2, I always thought there must be a recursion, like always. If we do something in n equals 2, then we find an algorithm in fixed dimension, and we just have to do it in the right way. But here with this quadratics, it's really, I didn't see how to do it.
One of the lemma you used were specific to the dimension tool, right? This reduction lemma.
Yeah. Yeah, so the integer hull computation thing is exactly what you need here in dimension 2, which does not generalize. The concave lemma generalizes to any fixed dimension.
So you have basically you have a concave lemma and a convex lemma.
Yes.
Playing them off. Is there any other case you know? Cubic elliptic curves. Is there a lemma for a class of cubics that says things work well, that's neither convex nor concave?
No, actually I don't. But I agree. I mean, this is exactly what you need, because general nonlinear integer programming, I mean, for me, this is completely hopeless. You need, even if you look at the continuous world in convex optimization, there are these very refined classes of convex functions that people use to build the algorithms. And so you need exactly the same thing, but even much more refined when it comes to mixed integer or pure integer. So in this respect, I fully agree. This is what I also hope, that we see some class structure with which we can go a bit further. Yeah, so this is why it's still a work in progress.
So can you extend this to a case where 2 integer variables and maybe a bunch of continuous variables?
This is another good question, which I didn't think about, but, well, actually, well, it's not so easy. Even in the continuous case, arbitrary quadratic functions you cannot do.
But you have Frank Wolfe, for instance, so that in this setting, Christoph's remark is settled.
Yeah.
Because any quadratic function bound below on
Yeah,
the
but that's not.
is
But that's not the only thing, right? We need here much more.
Sure.
So
I agree.
it is definitely worth looking at this mixed integer extension. Yeah, absolutely, I agree.
For the sake of lunch, maybe more questions to the speaker. Thank you again.